Glaciers move in two ways, by sliding into the ocean and by melting, causing sea levels to rise. Glaciologists face challenges in studying them due to limited specialized instruments.
You're listening to Shortwave from NPR.
Jessica Mejia's office looks a little different than most.
So the only way that we can get on the glacier to do our fieldwork is we have to fly via helicopter.
Yes, Jessica is a glaciologist. She's a postdoctoral fellow at the University of Buffalo, but her study subject is a couple thousand miles away on the Greenland ice sheet, a frigid mass that covers around 80% of the country.
Looking out over it in southeast Greenland, it's very jagged mountains on the edge of it. And then you see the glacier kind of cascading over these steep cliffs. And as you keep on flying, you fly kind of away from this whole cracked area that's kind of steeply sloping. And then you just see the horizon that's just flat with ice.
And that is where the helicopter drops Jessica's team.
And he was like, see you in a month. Good luck.
Their first step is to set up camp, which means shoveling out a flat space, pitching tents, and building a wall of snow for protection from the wind. Basically, they have to create a space in which they can survive on this glacier that takes its name, Helheim, from Norse mythology's frozen world of the dead.
It's almost kind of like another planet when you're out there because you are the only people out there. You know, you're very much alone. You just hear kind of the wind, or if the wind dies down, it's silent.
These glaciers are melting due to climate change, and that's causing sea levels to rise. This we know. But these glaciers, massive and motionless as they seem, are also moving. And what we don't know is whether faster melting on the surface might affect how fast the glaciers slide into the ocean, causing sea levels to rise faster, which, of course, would have real consequences for coastal communities around the world. That's why Jessica's team spends weeks living in this inhospitable space to research and try to answer this question, which, given how important it is, seems like it should have a lot of fancy tools. But it doesn't.
A challenge is that most of the instruments that we put out onto glaciers are not intended for glacier application because if you're going to market to glaciologists, you're not going to really have that big of a business at the end of the day. So
it's not an Amazon category somewhere with top 15 popular glaciologist instruments today.
No, but thankfully on Amazon, I have found the ice fishing kind of niche very useful for some applications.
So things like ultrasonic water sensors, Doppler devices, and weather stations that she actually freezes into the ice. Just don't ask her about the GoPro.
We were trying to basically put a GoPro on a string and kind of feed it into the moulin, and the knot did not hold, so there is a GoPro in a moulin in Greenland that will be there for probably a very long time.
Today on the show, how glaciers move and why figuring out how fast they're traveling has huge implications for people around the world. Also, what the heck is a moulin? I'm Aaron Scott, and you're listening to Shortwave from NPR. Jessica, I want to begin with how something as massive as a glacier, how does it actually move?
Okay, so glaciers move primarily in two ways. One is by kind of crushing under their own weight and moving internally within that block of ice. So that ice is deforming and stretching or pulling to move. The second one is by sliding. So we know the ice is sliding along the bed, but how much it is and how much it will continue to in the future is a big unknown because whenever there's melting at the surface, that water makes its way to the bed in many cases, and it can lubricate the bed and change how fast that whole chunk of ice, the whole glacier, is moving and sliding towards the ocean in the case of Greenland.
And if it's melting at the surface, how is it getting underneath?
So water produced at the surface, right, from melting, it will collect in either lakes or streams and flow kind of down the surface slope until it reaches something called a crevasse. A crevasse is a crack in a glacier. So that crack can actually reach the entire thickness of the ice. So it's over 100 meters thick. And so once it does, and there's enough water to keep that crack open, something called a moulin is formed. And that's basically, you can think of it as a hole that goes all the way through the ice. And it will basically act as kind of a funnel, collecting all this water from the surface that is going to flow in a river. And it looks like a waterfall going in a hole in the ice. And then all that water is reaching the bed. So it's reaching underneath the ice sheet where it can then lubricate that bed and control how fast the ice is actually sliding. And you can think it's not just one of these moulins, right, or these holes. It is a lot of them all over the place. And these streams and these lakes that form on the surface, they can drain quickly, they can drain slowly. The amount of water is going to be variable in how fast that water is getting into these things. So it's pretty cool, and it's really dynamic.
And so what is your research then? What are you trying to figure out specifically?
So I'm trying to understand what is that relationship between melting and sliding. So it's not very straightforward because there is a type of structure of that drainage system. The water is going to flow within underneath the glacier. And we can't see that directly, right? Because it's under a lot of ice. So you have to take all these measurements at the surface, like monitoring how fast the ice is sliding or how much water is going into them, and try to like infer what that structure of the drainage system is just based on these relationships that we're seeing.
And I mean, how do you do it? I mean, this is a huge expanse. How are you measuring how much water is flowing underneath the glacier, how much the glacier is moving, and then trying to connect the two?
So you can kind of zoom into a catchment scale, just like in regular hydrology. A catchment is kind of a geographically, like topography bound area that's draining into, say, a river. And so there is an area that's draining into one moulin. So if we zoom into that level, we can try to measure how much ice and snow is melting on the surface, how much water is actually making its way into the streams or rivers that are flowing into that moulin. We can monitor, say, the water level within the moulin, which is telling us just about pressures underneath the glacier. And then we can install GPS stations on the ice, on the surface, and monitor how fast that ice is moving and how fast it's sliding.
So with, climate change and warming temperatures, the rate of melt is increasing. Can you tell us a little bit about how the data you're collecting and what you all are finding is fitting into this bigger picture of melting glaciers, sea level rise, and really the implications for the rest of us?
So with satellites, we can see that we are losing mass, and we can see that it has been melting since about the 90s. We've been losing mass, and it's been accelerating. A lot of really great work has shown that we are going to have a lot of melting in the future, whether we stop carbon emissions yesterday or not. That's destined at this point that we're going to be losing mass and having more melting, at least throughout the century. So with that comes a few things, right? It's with increasing amount of water reaching the bed of glaciers, how will that impact how fast it's sliding? In, say, alpine glaciers on the sides of mountains, that subglacial drainage system I talked about earlier, that can really compensate for that increased meltwater so that you can keep on melting and it doesn't really affect sliding anymore. However, in Greenland, we're showing that that's not what's driving these changes in sliding, especially the slowdowns. So it's really unclear whether the Greenland ice sheet will be able to just accept this meltwater and it not affect sliding like a lot of other work had suggested.
So you're saying that in steep mountains, more meltwater doesn't make the glaciers move faster because all that extra water is able to drain out of the system. But that might not be the case in places like Greenland, where meltwater could actually accelerate how fast the glaciers slide.
Exactly, that it could accelerate instead of just staying the same no matter how much melt you're putting into the system. Exactly. And then also, we know that the area of the ice sheet that's melting is getting further and further inland. What was it? Just in 2021, it rained for the first time ever in recorded history at Summit Station, which is in the middle of the Greenland ice sheet. This research station has been around for a while, and it had never, in human knowledge, rained there, been warm enough for precipitation to fall as rain. So things are changing super rapidly in Greenland. And while that doesn't seem like it matters, it will very, very much matter to have those accurate predictions once communities are actually implementing mitigation techniques or strategies, mitigation strategies. Then knowing how long you have is extremely important and will cost millions or even billions of dollars if you don't have accurate timescales for which those things need to be implemented.
So, right now we have these complex models that are predicting that ocean levels will rise a certain amount at a certain speed based on how fast we're seeing glaciers melt. Would your team's research potentially change that forecast and change those models? Would finding that this melting makes glaciers move faster, would that then affect our understanding of how fast ocean levels are rising?
So potentially, yes. It's going to affect probably the rate of the contributions to sea level rise from the Greenland ice sheet in particular. And so that becomes very important for coastal communities because whenever you're having mitigation efforts and local governments around the world are planning and designing infrastructure or relocating communities or doing a wide number of things, is it 10 years or is it 20 years, right? So that's wherever the precision becomes more important for people, even though in 100 years, we're going to see higher sea level rises, right? But including the hydrology and how the melting influences this ice motion, it becomes then important for those rates.
So the accuracy, so it will help these communities know this is what's going to happen in 20 years, this is what's going to happen in 30 years, we need to plan accordingly.
Yeah, so a better estimate, exactly.
And so, these ice sheets are huge, and as you said, we're locked into them continuing to melt and melt faster for decades at least. It seems like that could be very overwhelming. I'm curious what it's like to live with that and what gives you hope and keeps you, getting back in the helicopter and flying onto the ice sheet for weeks at a time.
It is overwhelming. I think in general, there needs to be a better connection between scientists and policymakers. Mm-hmm. But I do know that the overall goal of understanding these systems is super important for especially the mitigation strategies. And if we don't do this work, then these communities don't have as much of a chance, right? Mm-hmm. It's just going to be more difficult. And with already the inequalities in distribution of resources, especially to poorer communities or communities of color globally, we already know who gets the short end of the stick. My goal in getting into glaciology was to use my skill set in whatever way that would make the best impact. And I think I found my puzzle piece, but it's not just me, it's not just you, it's all of us collectively.
Thank you so much, Jessica, for taking us out onto the ice sheet.
Thank you for speaking with me today. I really enjoy sharing the work that we're doing.
This episode was produced by Burley McCoy, edited by Giselle Grayson and Gabriel Spitzer, and fact-checked by Britt Hansen. The audio engineer was Josh Newell. I'm Aaron Scott. Thanks for listening to Shortwave from NPR.